front here, come in, and please welcome Guy to take us through the memes.
Well, welcome everyone. I apologize in advance. I'm losing my voice. You can thank the flu that's been going around for the last 3 months for that. But I have amplification, so that'll compensate. Welcome to my talk. This is Modern Problems Require Modern Solutions. It's about vector databases and embeddings, and specifically I'm going to be embedding images. And I've got some principles or ideas that I really kind of want to, they're not in my slides, but I want to talk about them before we get started. We're all doing AI stuff, right? And I want to show really four things here. One is that in order to do the AI stuff, you do not have to plop down a credit card for an OpenAI API key or anything like that. You can run this stuff locally. So all of my demos run locally on this MacBook. I don't need to get some big cloud instance. It all can run right here on your computer. So two is that it's not, what do you want to say here? It doesn't need to be in Python. Like all this data, right? How many here are Python developers? A couple of you? We're mostly JavaScript and Java developers. I mostly do JavaScript, but I've done a lot of Java in my career as well. All my demos are in JavaScript. So they're easy to use. You can run them locally. You don't have to learn a new programming language. You don't have to slop down a credit card. And the other thing that I like to do is I like to get down to like first principles. And so I'm not a particularly mathy person. Not because of aptitude or anything, but because I just haven't studied it. And so what I like to do is get into these data science tools, get into all the tools I use really, and get a level beneath and get an intuitive understanding of that level beneath so that the level I'm operating at makes sense. And so we're going to go down and understand what embeddings are, how vector databases work, how you can create your own embeddings, how you should do it. I'll show you how to create your own models to build your own vector embeddings and then tell you that you shouldn't do it. Because the smarter people than me have done this, smarter people than you have done this. There's lots of really smart people out there. Let's reuse their work and stand on the shoulder of those giants. So that's what we're going to do today. We're going to talk about embeddings, vector databases, and we're going to have a demo. The demo will be interactive, which means I'm going to ask for volunteers to come up to stage and have their photo taken, and we'll see what meme character you are. So if you're shy, leave now. All right. My name is Guy Royse. I'm a developer advocate at Redis. Here's my socials. I like to say that there are three things on this slide that matter. One of them matters to you, one of them matters to me, and one of them matters to my boss. That right there. So my boss would like you to know that Redis is more than a cache. It's more than just a key value store. It does cool things like vector search. And so it can be a vector database as well. We're going to talk about that today. All my demos are in Redis for all the obvious reasons. Now, the thing on here that matters to me are all those social links. So I judge my worth as a human based on how many people follow me on social media. So if you're on Blue Sky, or if you're on Twitter still, X, Twitter currently known as X. That's what we'll call it. Give me a follow, love it. And the thing on here that matters to you more than anything is that GitHub URL right there. And there'll be a QR code later to the specific repo that we'll be demoing. But that's where I have all my code and demos and exercises and things that you would want to actually clone and use as a basis for building something real. So whenever I give a talk about any of this AI, machine learning, data science stuff, I always like to put a little bit of a qualifier on there. I don't always pretend to be a data scientist, but when I do it on stage. I am not a data scientist. I am not particularly mathy. And I don't have training in this. But what I like to do is I'm a fan of data science. And what I like to do is I like to dive into the details and understand it and get that intuitive understanding of it. And then I share it. So that's what we're doing here today. Anyone here a data scientist? Okay, so one person. So what I meant to say is I'm totally a data scientist. And you should listen to everything I say. I'm an expert. And if he says I'm wrong, then he's wrong. And then we'll fight it out afterwards. Not a data scientist at all. We got four main topics we're going to cover today. Is 4 agenda items a lot? Well, it depends on the context. For a talk at a conference? No, not at all. For a talk with your boss? Yes. We're going to talk about what an embedding is, and get that intuitive understanding of what embeddings are. We're going to show how you can use embeddings to do things like semantic search and semantic caching and RAG applications. Mostly we'll be focusing on the search aspect in the demo. We'll look at how you can make your own embeddings and why you shouldn't. And then we'll end it all with a look at some code that actually does this, and then actually show that that code works and does a thing. And so that's the talk. So we'll start off with what the heck's an embedding. Am I the only one around here that knows what an embedding is? You might notice that actually these images are bigger than the meme images usually are. I ran them through Photoshop and upscaled them and then had them do generative AI infill. And I think it's really funny that the guy in the bowling alley with the pistol from The Big Lebowski, apparently there's a guy behind him with a rifle as well. You can see it up there. I don't know if it just decided it needed a rifle barrel in there. It's the most American slide ever. To understand embeddings, I want to talk a little bit first about data. And so we've got two types of data that we run into in our applications as developers. Just kind of in the world in general, there's structured data. We know what structured data is. This is the stuff that we put in our relational databases, in our key value stores, in our caches. And we you know, if you're using Redis as a key value store, you're using MongoDB as a document store. If you're using MySQL as a relational database, that's structured data. It's things like numbers, like the year or the date. It's things like strings, like varchar 24s, that sort of thing. Or it's locations and just these sorts of very specific measurements of things that we care about. And we can then query them very easily using things like SQL and that sort of stuff. And then there's unstructured data. This is data that's easy for humans and until recently was hard for computers. This is stuff like bodies of text, like I've got an article. There's data in there. We need to pull that data out. How can we pull that data out? It's unstructured. Humans can read it and pull it out easily. But it's hard to do a select star from document where. That's not something that most tools do. Images. What sorts of things are in these images? There's data in there, but it's unstructured. We need to pull that out somehow. And audio is another example. And there's several other examples, video, that sort of stuff. But this is data that is easy for humans and harder for computers. It's become easier for computers in recent years. Now, structured data, we know how to deal with structured data, right? We've done this a lot, right? You take, and put your structured data in SQLite, right? That's where everyone puts all their data. No, maybe not SQLite. Maybe you're using Access. No, you're probably using Excel. I actually was hanging out at a conference a couple of years ago, and a friend of mine said, if it's not running on COBOL, it's running on Excel. There's a lot of truth to that statement. But structured data, we know what to do with structured data. This is a solved problem. It's been solved for decades. It's been solved since I started my career. Unstructured data is a little squishier. We need to do things to pull out meaning out of it. And so this is what an embedding is. An embedding contains the semantic information in unstructured data. So we have a meme here. Don't need to debug your code if it doesn't compile. Think about it. It's got text, which is unstructured, and it's got an image, which is unstructured. And we can use embeddings to encode that meaning, that the things are in it. So, for example, embedding the image might have encode the idea of someone pointing at their head and smirking. An embedding of the text might encode the idea of debugging and compilation and negation. These are semantic elements. These are meanings. That's all semantic means, is meaning in these images. This is data that we can extract from that unstructured data into something structured. In the case of text, usually you need to do some sort of processing of that text beforehand. So if you have, I have a version of this demo where instead of doing meme images, I do text of Bigfoot sightings. And in the Bigfoot sightings, I have to go in and summarize the accounts because sometimes they can be quite long. And so I run it through an LLM and I summarize it to shorten it, so that when it's tokenized into all of its individual components, it will fit into the model that I'm using. And so we tokenize the text after we summarize it, And that tokenization finds all the words basically, but it's also the punctuation, and sometimes you have like a compound word like Bigfoot might be a single token because it's Bigfoot, the big hairy guy, but it also might be big and foot. And so it'll pull those tokens apart. And then those tokens are handed into an some sort of a transformer and some sort of AI model that will then create an embedding. And that embedding is nothing more than an array of numbers. Now I have 12 numbers here on the screen. They're usually bigger than that. For the Bigfoot, for the text embedding stuff that I've done in the past, the model I use, it creates an array of 384 numbers. And each of these numbers represents some sort of feature that the model has identified in the text. This could be a idea of debugging and compilation, and it's a score from like -1 to +1 of showing how much that text has the concept of debugging in it and how much it has the concept of compilation in it. Or it could be, in the case of an image, similar things like, is the person pointing at their head or are they smirking? In the case of images, you usually need to transform them. The models that take images want images in a particular resolution, usually square. And so you need to go in and either crop it or scale it or add black borders on the side so it looks like an old show on a widescreen TV. And that transformation, in the case of image embeddings, goes through a series of convolutions using a convolutional neural network. This is the main way that I know to do it, and I'm going to talk about it in greater detail. But this is a process of hierarchically decomposing the image and saying, well, I found these lines. Okay, these lines group together to represent an eye. Okay, there's 2 eyes and a nose and a mouth. Okay, there's a face. And so it hierarchically decomposes that image and identifies the elements in it, the features in it. And then you can run that and get an embedding. And much like the text, you can get numbers that represent things about that image. There are some models that are really cool that are multimodal, where you can give it text and it will give you numbers. And you can give an image and it'll give you numbers. And if the image and the text are about the same topic, those numbers will be similar. And so you can put an image in and then compare it against text. Or you can give it text and then find images. These numbers represent features that the model has identified. I'm arbitrarily going to point out 2 features because it makes it easy to think about. But there are hundreds of them. And these are meaningful to the model, not meaningful to the humans. So I'm saying that there are 2 columns in here for an image here representing or 2 elements, 2 values in that array that represent how elderly the subject is in the image and how alcoholic they are. I don't believe the model actually has these concepts expressly written out that way. But it does find old people versus young people, and it does find images with alcohol in them and images without. And so, but this vector that you get out when you create this embedding is rankings of all the features that's identified, from a +1 to a -1 value. And so elderly and alcoholic might be an example of that. So in this picture here, we've got Leonardo DiCaprio with his glass out saying cheers, right? And that's a good time for me to take a drink of water. And so he's clearly got a coupe glass. There's some sort of cocktail in there. Definitely alcoholic. He's not that old in that picture, but he's not young either. So slightly below the 0 line for elderliness. Another image could go through the same algorithm, the same model, the same process, and get different values. So now we have here Grandma discovers the internet. One of my favorite memes. And she's clearly very elderly, but there's no indication in this photo that there's anything alcoholic related. And so it's got a low score there. And so it's just a matter of ranking these. There's more of them than just 2, but we're going to look at 2 so we can understand how these things work. So you can think of these vectors, these embeddings you get back, this array of numbers, as coordinates. Our simple example here has a coordinate of 2. We got alcoholic and elderly. And that's because it looks better on the screen than the model that I use, which has 512 dimensions, which is kind of hard to put on a screen. But what you can do is you can just plot them out on a chart. And so the degree to which the image is alcoholic or elderly becomes a point on a graph. And so we see here on the top right, no, it's not showing up there. I got to do this. There we go. So up here, we've got people with alcohol. So you got the world's most interesting man. He's got a bottle of Dos Equis, and you've got Leonardo DiCaprio there with his coupe glass with a cocktail in it. Those are ranking higher on the alcoholic thing. Here you also have what's really a really funny meme, a very drunk-looking baby with a pint. And so he's clearly young, but also there's a lot of alcohol pictured in that image. And so we're plotting this out on a graph. And so you can think of these vectors, these embeddings that come out of these models as coordinates in a space. It's a hyperdimensional space. This is a representation of it. So you can use these coordinates then and see how similar they are. And this is how you can match images and embeddings to each other. So we've got for example, let's take these 3 images here. We've got the success kid with his fist on the beach. He's like, yeah, sandcastles, right? You've got the world's most interesting man who's just sitting there looking all distinguished and drinking his Dos Equis. And then you've got SpongeBob making fun of everyone. Got the mocking SpongeBob. And these images become embeddings, which are numbers, which can be stored in a database. This is what a vector database does, is it stores these arrays of numbers. And then if you want to query it, if you want to search for it, you can take an image, a query image, or text, or whatever you're creating embeddings on. And we'll take a picture of me and say, who do I look most like in this thing? It creates an embedding off of my image, and then when I can query the database, I can compare the numbers in the embedding next to me to the numbers for the embeddings of the embeddings of all the other images. And whichever one is closest is more similar because they have the same scores in the same places. And so the first time I did this, I came out as the world's most interesting man. That's probably not going to happen today. Lately, I've been coming up as the dad in that meme from American Choppers where they throw the chair, like the dad's yelling and the son's yelling and they throw a chair. And, right? I'm the dad. So maybe maybe I'm scary and no one should be sitting in the front row. But this is fundamentally what semantic search is. You shove all these vectors in a database and then you can compare them. How do we determine if a particular vector, a particular embedding is similar? A particular set of coordinates, how are they similar? Well, there's a few different ways you can do this, and they're all way more intuitive than you would think. The easiest way, I think the most obvious way, is Euclidean distance. That's a fancy word that says draw a line between the 2 points and measure it. You're using Pythagorean's theorem. You're drawing a triangle in a lot of dimensions, but you're drawing a triangle and you're saying which line is the shortest? The shortest line, the shorter the line, the closer. You're getting your nearest neighbors. Easy peasy. This is really easy to understand. If the numbers are similar, of course the points are going to be close to each other. Another option is cosine similarity. The idea of cosine similarity is you go from origin and you draw a line to each of the points, the point you're querying and all the points you want to compare it against. And then you measure the angle and you take the cosine of that angle, and the smaller the number, the closer they are. Also, pretty straightforward. And what these do is Euclidean distance tends to find things that are nearby but maybe next to each other. And so it works on sort of a magnitude. So if you've got something that's towards the center, it might be a little more generic, and as further out, it's a little more specific. Then Euclidean distance is going to go side to side and find things that are similar that are next to it, kind of at the same level of abstraction. Whereas with cosine similarity, it's looking at direction, and so things that are close to each other, but maybe they're further apart. So something that's really close to the origin and something's far out, like maybe the idea of intoxication is close to the origin, and alcohol is a specific type of intoxication that's going to be further out, and so a cosine similarity will match those concepts up better. And neither of these are actually perfect, though. And so there's actually a third way, which I don't have a picture for, but you can do the inner product of the two embeddings. And that kind of hits a balance because the more in line they are, the smaller the inner product, but also the closer the points are, the more similar the inner product. And so that creates a nice balance between the two. I found in practice that whenever I do inner product, the model that I have identifies me as grumpy cat. When I use Euclidean distance, it tends to identify me as the most interesting man in the world. And when I use cosine similarity, it tends to identify me as the dad from the American Choppers meme. Another way that you can use this is you can do a simple area calculation. This is useful if you want to use semantic caching. So you can say, I've got a point, give me everything that's within a radius of that point. Because if things are too far away, I don't care. They're not similar enough, I don't want any results. So, you're querying from it and saying, give me things that are within a similarity threshold. And you're literally just saying, here's my point, draw a circle, give me everything that's inside that circle. Except it's a hypersphere, because it's got 512 dimensions. But conceptually, it's a circle. So this is how you can measure that similarity. Now, building indices off of these can be a bit of a challenge because they can get big. And so you got two choices in Redis. There are other solutions to this. These are the two I'm familiar with. You've got a flat index, and that flat index is it's a straight up brute force approach. It's perfectly accurate, but when you get to about 1 million entries, it starts to slow down. Now, for a lot of applications, 1 million entries is plenty. But if you have more, then you might want to look at something like a hierarchical navigable small world to build your indices. This creates a layer, a series of planes with particular points in the graph. If you picture that two-dimensional space, it's like, well, we'll take 3 of these points and they'll be the entry points, or 5 or 10 or whatever, or 10% of them. And then when you look for a close point on there, and then you go down to the next level and look for a close point, and go down to the next level and look for a close point, and you hierarchically search in a tree-like fashion through the layers. And this gives you better performance, but does create some accuracy issues. So you're trading off accuracy, speed, and space. And these are your choices. The simple metric is when you're doing small, easy things, use flat. When it gets bigger, use HNSW. So this capability opens 3 common use cases. One I've talked about 2 of them a little bit already, but semantic search is the idea that you take embeddings and shove them into a database. So here we've got 3 meme text from 3 memes. Deletion is 100% file compression. Facts. TypeScript is just JavaScript for C# devs. Changed my mind. I actually personally believe that. And code doesn't compile, compiles it again. And so you can take this text, create embeddings off this text, and store them in a vector database like Redis. Then when you want to go search, you type in your text, you create an embedding, and you go and using either Euclidean distance or cosine similarity or inner product to find things that are nearby. This is the basic use case for vector databases, is finding things in unstructured data that matches unstructured data. You can also use this to implement semantic caching. This is a nice way to get a lot more value out of your LLMs. LLMs can be a little expensive to operate. I heard a great story about a auto dealership in the United States that had a little chat bot using an LLM behind the scenes. And they didn't put any constraints on the topics it could talk about. And so devs found it and started asking a bunch of questions about Python. And then they're like, why is our bill so expensive? And so semantic caching can mitigate those sorts of problems. The idea here is you've got some user that has a question that they want to ask the LLM. In this case, Grandma's wants to understand what a dank meme is. And she's going to ask an LLM. But other people have asked similar questions before. And so out there in your vector database, you have the answers to other questions. What is a dank meme? I don't understand dank memes. And those questions are associated with embeddings, and then the response that the LLM gave is there as well. And so what Grandma can do is her question gets embedded, and you hit the cache, and you say, and you do a search and say, has anyone asked a similar question before within a threshold? If the answer is yes, you've got a cache hit. Just return the results, and you don't have to call the LLM at all, which is great. Saves you tons of money, saves you tons of time. However, if there's not one out there, then you ask the LLM, return the result, and add it to the cache. So this is the basic cache-aside pattern that we've probably all used in our applications before, but we're using it for caching the results of an LLM semantically, as opposed to caching, say, an API call where someone is checking the weather. This can be a great way to save a lot of money and provide better performance. The third one that everyone's talking about, I'm sure there have been talks here this week on RAG. That's retrieval augmented generation. The idea behind retrieval augmented generation is similar. It's used taking advantage of vectors as well. It's another way of making LLMs more productive. It can be combined with semantic caching in front of it. And so someone asks a question, can you explain to me what a dank meme is? The LLM, however, doesn't know anything about meme culture. Totally not true. It was trained on the internet. But we'll pretend that the LLM doesn't understand meme culture. And so it doesn't have any context about this sort of problem. But there's a database full of context, documents out there that explain all about meme culture. And so you can create embeddings against those documents. Grandma can ask her question, create the embedding, go out and hit and say, give me context, give me documents full of information about meme culture. And that is then handed to the LLM along with the query. And you literally, it's like you've gone into ChatGPT, copied a web page, the text of it says, given the following information, colon, and then you paste a bunch, some blog post entry in, answer the following question. What's this person talking about? So you could literally create like interrogatable documentation this way. You're just giving the documentation to the LLM, and then you're asking a question. This is a great way to encapsulate all sorts of business rules and proprietary information that the LLM might not be aware of. And then, of course, the answer is returned, and that answer is eminently cacheable using semantic caching. So this is retrieval augmented generation in a nutshell. It's one of those things where people are like, this is big advance. It's actually not that complicated. You're literally just going out and querying. You wouldn't even have to use semantic search to do this. If you had like a database full of keywords, you could just go out and query a relational database to get documents and send it along with the query. So obviously semantic searching makes that better because documents tend to be unstructured, but you could do this without. You just have to retrieve it from somewhere and pass it along with the request. So that's sort of what vector databases are and do. That's sort of what embeddings are. Let's go to the next section of the talk, which has the parts that you shouldn't do. Creating embedding models yourself? Nah. Using existing embedding models. I should have used the Drake posting one instead of Kombucha Girl, but regardless, you should use existing embedding models. This is a fairly well solved problem, but if you want to know how they work or how they can work for images, I'm going to go into the details. So it's a little bit of one of the things that I like to do is I like to make sure I don't leave anyone behind. And so I'm going to start with your basic neural network. Now many of us, probably most of us, have seen this picture before, right? You've got an input layer, and these are just numbers. And then those numbers for each layer are handed to every node in the next layer, and computation happens on them, and they're handed to the next layer, and computation happens to them until you get an output layer. This is your basic neural network. You shove numbers in as x's, you get numbers out as y's. It's a function. This giant function of a thing draws lines, generally. Your simplest neural network, we're going to boil it down to the simplest that you can, is a basic neuron. So a neuron in a neural network normally has multiple inputs, but this one has one. So it has an x as an input. And it has as an output a y. And so this is f of x equals y. This is a simple function. Inside of the neuron, there are two values. There's a weight and a bias. And these are computed using some sort of backpropagation training algorithm when you build the model. It's a bunch of calculus that frankly I don't understand, but I have learned to say stochastic gradient descent. But the math in here, in terms of computing what comes in and out, is actually pretty simple because the formula is the input times the weight plus a bias. And that gives you an output. And if you're savvy, you might recognize this formula as y equals mx plus b, which is perhaps the only thing I remember from high school algebra. And what this function does is where you get m is the slope of the line. So this draws a line, and it's determining the angle of that line. And then the bias is sliding it back and forth across the y-intercept. And so this lets you create lines that can move all over the place and are useful for models. And so you get lots of linear functions. Now there's a limitation with this, which is that if you take a linear function and then hand it a linear function and hand it to a linear function, you're going to get lines, right? Linear functions beget more linear functions. You're not going to be able to get any curves to draw anything interesting. And so the way you solve this problem in a neural network is use what's called an activation function. The activation function is applied after you've done the math. And so we've multiplied the input times the weight, added the bias, and then we run it through an activation function, and then that can get us lines that start curving. Couple of choices here, and then there's really the one everyone uses all the time. You can use a sigmoid. This takes you from approaching 0 to approaching 1. And so this gives you degrees of encouragement. So the output of that neuron is going to be either just kind of like, I don't care, to we really like this output. Hyperbolic tangent is similar, but it goes from -1 to +1, and so it can actively discourage the output on next node. It can actively discourage this particular input to other nodes. And then what everyone has found in practice works the best is rectified linear units. And this is super easy. It's just, if the number's positive, it's the number. Otherwise, it's 0. Ignore negative stuff, just do positive stuff. And then we can activate harder. So this is what's happening. Excuse me. This is what's happening in a neuron. So this is what's happening in a neuron. But of course, a neuron has multiple inputs. It doesn't have a single input. And so here's one with 3 inputs, which is also not terribly realistic, honestly, because they often have hundreds or thousands. But we're going to do 3 because it fits on the screen. And what you're really doing is you're multiplying all of the inputs times all of the weights and summing them together. So input 0 times the weight 0 plus input 1 and times weight 1, et cetera, adding the bias and getting your y. Or in the most mathy part of the slide here, I actually used a sigma. So it's the sum of the inputs times the weights plus the bias. So that's how a neural network works internally. Now, these can be used to just draw a line and build basic binary classifiers. You can create more general classifiers. You can do regression and all sorts of things like that. But we're going to talk next about convolutional neural networks, which is a specialized type of neural network. How am I doing on time? I think I'm doing okay on time. I got 18 minutes. This will be fine. So this is a convolutional neural network, a representation of one. The idea of a convolutional neural network is it has limited connections between the layers, and it strips out hierarchy. And so the idea is you have an input, which is an image. And it's shown here as a little two-dimensional box because images are, our eyeballs see 2 dimensions. Each eye sees 2 dimensions. And then you've got, and so the input is just pixels. Or more accurately, numbers representing pixels. Well, I guess pixels really are numbers too, aren't they? And then it goes through a series of filters that identify particular shapes within the image, smaller pieces. And so this image here is 5 by 5. These filters are 2 by 2. And so it's checking every 2 by 2 space on the image and saying, does this image have a pattern that matches what's in the filter? And then you get an output, which is a map of those values. You can run those through pooling layers. The pooling layers will sort of concentrate it down and take a larger thing. And it's really kind of like just taking an image that's 1024 by 1024 and making it 512 by 512. And it helps smooth out irregularities in the image. It's kind of like squinting at a line and then it becomes straight. That's the way I like to think of it. Then you can take those pooled layers and you can go through this process as many times as necessary. And then you can flatten it out. And these are your features. These numbers then that are flattened is the embedding. And so through this process, it hierarchy identifies features in the image, going from lines to eyes to faces, from lines to curves to cups, to all the things that might be in the image. And then these features say, is there an alcoholic beverage in here? Or is there an elderly person in here? And you get those sorts of attributes. and they become numbers from -1 to +1. A better way to show this sort of filtering here, here we've got my attempt at a troll face. It kind of looks like a troll face. And what you're doing here is that filter is panning and scanning across them and then creating a map of everywhere that filter applies. The most obvious one, the one I think really shows it off, is the filter on the top right, up here. Hang on, where we go? There we go. Right. So that's two dots on the right in the center, which matches the eyes. And then you can see the map shows the two eyes right where you would expect them to be. Is that great? So this is what it's doing, is it's sort of identifying, well, here's a map of where all the eyes are at. And then you could have another map or another filter that says these are a pair of eyes and a nose and a mouth, and that's a face, etc. Decomposing it. To make this a little more visual here, here's our troll face. And I've got a little animation here that shows how this works. And so we've got a little 3x3 filter, matches the pattern. Nope, doesn't match. And so it just pans and scans. I should have automated this so I don't have to click the button so many times. And when you get a match where the filter matches the input, then you mark it. And see, there it is again. And so it's just scanning along and building a map where that pattern is matched. Come on. I'm going to break my pointer. Of course, we're not really doing existence, not existence. These aren't Booleans. These are numbers. And so if we look at these as numbers, I am saying this is a pure black and white image, and so you get 0 and 1. If it had any grayscale in it, it'd be values from 0 to 1. If it was a color image, there'd actually be multiple layers. And you can think of it as a cube because you'd have a red channel, a green channel, a blue channel, and possibly a black and white channel as well, which is how our eyes work. But you have all these numbers that represent the color value that's there. And then the filter is representing some intensity as well. It's not just on or off. It's got some graduation to it. Now, I've just hard-coded all 1s and -1s in the filter. And there's a little number under the filter, too. And I'll talk about what that is in just a moment. And then the output then is numbers. And as you see, when you apply the numbers here, it's finding things that are like like the 3 dots matches enough that it gets a number, but it's not as hard as the other matches. And behind the scenes, what's happening here is this is that same y equals mx plus b calculation that's happening. So the x is your input. That's your numbers. And so we look at like the top 3, the top left corner is 3x3. And we multiply it by the weights, and then that gives us a number 0. Actually, it probably gives us, yeah, it gives us 0. I think it might give us, yeah, it gives us 0. Definitely gives us 0. And so we do that same calculation, add the bias, and then run it through ReLU. And that gives us our output. So we're applying that same logic. So those filters are really the weights going into the next layer. That's what a convolution network is doing behind the scenes. Pooling is pretty easy to understand. You go through let's say we're going to do a 2x2 pool, which is going to have the size of that image. And we're going through, and every 2, we're looking in there and saying, is there data in there? In this case, in the simplified case. If there is, then we put a block. If we don't, there isn't. And again, this is not really happening with Booleans here, it's happening with numbers. And so we take our previous numeric output and we look, whoops, go back. And if you look at the first 4 squares in the top left, right up here, right? There we go. We got 0, 0, 0, 1. And so in the top left corner, we put a 1. We take the maximum number in that space. There are other options. You could take averages and stuff like that. I went with max, although in this example, it doesn't matter because max or average would have been the same. Well, average wouldn't because it'd be zeros, but anyhow, I did max. So once you've gone through these pooling layers, you can go through these multiple times, and then you take the output of that pooling layer and you flatten it. And flattening is just a matter of taking the values that are in there and putting them into a flat array. This then becomes the embedding. Clear as mud? Excellent. So just a reminder, You can build these. I've built these with Keras before. It's not that hard, honestly, and it's fun. And you're that dev in the middle there saying, yeah, I want to check that out. That sounds fun. Go ahead and do it. It's fun. Try it out. But don't do it in production. Let other people, building models is a lot harder than you think it is, right? One does not simply create their own embedding models. I'm a developer, not a data scientist. You want to work with, like if you got data scientists on your team, you're working with them, work with them to do this kind of stuff if you need something custom. But a lot of the models out there are perfectly suitable for what you want to do. So that's pretty much it for the information part of the talk. I'm going to do a demo here in just a moment. I love Chappelle. He's hysterical. And so I got a little demo, and I'm not saying I'm going to use Redis, but I'm going to use Redis. This should work with other vector databases as well, but I'm here as a shill for the company, and so I'm going to use my company stuff. What I've built is fairly straightforward. I have built I've got Redis out there. I've built a little meme loader. What the meme loader does is it looks in a folder. It creates an index in Redis for doing vector searches. And then it pulls a bunch of memes from a folder, takes the title of the image as the title that it puts into Redis, it creates an embedding, puts the raw image, and shoves that into Redis in a key, in a hash. I've then built a client, which you can go in and take your photo. The hardest part about building this demo is actually getting my camera to work with my web browser. The code itself is actually pretty straightforward. But it'll take your photo, and then it'll send it up to a little REST API written in Express, where it will make an embedding of that photo, and then search for a matching embedding in Redis, and then fetch the image and return it and take fun pictures. So I want to show the code because I want to show how easy this is, but I also want to show the demo. So let's go ahead and go to the code first. And we'll just hit some highlights in the code. So this is almost not worth showing here because this is really just code that scans the folder for images, and then calls an embed function to create an embedding that's imported from another file, and then adds it to Redis. So this is just looking at files in the file system, embedding them, adding them to Redis. The embedder is, I think, the interesting part. And is that text big enough? Is that better? So this is my embedding code. I'm using a Hugging Face Transformers library in Node. I'm calling the pipeline function and telling it, I want image feature extraction. Here's the model I want you to use. And the data type is a 32-bit floating point number. And then I've got and that creates my extractor. And then when I want to embed something, I literally hand it the path to the image on the file system. I use that extractor, give it the path. It will convert the JPEG or the PNG to all the stuff that it needs to, and then return an embedding. The embedding part that I care about is the data on there. And so this is mostly to make TypeScript happy. So I cast it the appropriate type. And then here I'm turning it into a buffer so that I can use it with Node Redis. That's the entire code for creating the embedding. It all runs right on this laptop, which is pretty cool. The actual searching involves me creating an index. And so to create an index here, I call ft_create. Indexes have a name. It's passed into the function. And then I'm taking the title of the image and saying that's a text search. And so that's full text search. It's a whole other topic. And then my embedding is just a field and a hash in Redis that's an embedding. I tell it that that's a vector to use the flat algorithm, that the type is a 32-bit float because that's what the model returns, that the dimensions are 512 because that's what the model returns, and I pass in a distance metric. And I've actually made it so we can change the distance metric in the demo. And then the actual matcher code is just a matter of building a query. And I know I'm hitting this fast. It's all out in GitHub. I just want you to show you that it's real. So we've got a simple query where we can pass in star, which is give me everything. And then that goes into these parentheses right here with the little fat rocket there. And then in square brackets, we put in the actual embedding query where I want k nearest neighbors. I want the first neighbor. I only want one. And then I have the field called embedding, which is where that vector's at. And $blob is going to be brought in as a parameter and interpolated into that string later. And you can see down here in my options, there's blob embedding. And then it's just a matter of calling search with the index name, the query, and the options. And then it will return results, and then I parse them and put them on the screen. So that's the code. There's not a ton here. I've got some client code. None of you care about the Svelte code, the crappy Svelte code that I wrote, so just ignore that. But the important thing here is the embedding. So let's go ahead and show that this is real. I'm going to do a docker compose up and cross my fingers. Yeah, allow whatever you want. I don't care. So the meme loader gets built, and what the meme loader does is it waits for the server and the client to be up and for Redis to be up, and then the meme loader will load all of the memes right in real time. So I know it takes like maybe 20 seconds on my MacBook to load. I have 72 memes in there. I was given a meme last night that is a Swedish meme, which is like the is it Skogstyrken? Is that the right word? Yeah. I have no idea why it's funny, and I wanted to put it in there, but I just didn't have time. So apologies. But they're all the classic ones, and this is taking longer to start up than I was hoping, so I'm stalling. We can take a look at Redis while it's doing that. Oh no, it's not. Redis isn't up yet. Okay, come on. I don't want to go over. I want to be a good citizen. Okay, so the meme loader is doing its thing. I think it's rebuilding all the images, which it shouldn't be doing, but whatever, Docker. You do you. Well, while we're waiting for that to go, I'll go through the rest of the slides here. So, me when I see a talk, but before the demo. I think the skeptical third world kid is probably my. I like this meme almost more than I like Grandma discovers the internet. So, if you are interested in trying this out, we'll demo it here once it gets loaded. But QR code to the repo. It's got the slides for the talk and everything, and it's got. And you too can do Docker Compose up and have to stall on stage. I work at Redis, of course. You can check us out at redis.io. We've got a course at university.redis.io. If you aren't familiar with Redis, you want to get deeper into it. We got some introductory material there that actually I had the misfortune of recording, and you can enjoy. I've gotten great feedback, even though I personally felt like I sounded a little flat, but it's been very popular. And we have a Discord server which I help manage. So if you have questions about the stuff, you can ask on there. Let's see, are we up and running yet? What the hell? PC load letter. That's a great idea. I could take a couple questions here really quick so that I'm ready to go over. How much slack do we have in going over? It's lunchtime, right?
No, it's a short break only.
Okay. Well, I'll be as good as possible, but I totally want to show this working. Yeah, any questions? Your stunned silence is very reassuring. Yes, sir.
So you're discouraging people from creating their own embedders, and that's because you will have to train your own models.
Yeah.
So it's not just like you're transforming text simply. You need to like extract this data from the images of the text with a neural network.
Repeat the question.
Yeah. So the question is I'm discouraging people not to create their own embedders, and that is correct in general, particularly for image embedders. There's plenty of really good ones out there. A lot of them are identifying features in them, features that are common to lots of things. You can do that. It's just a lot of work, and it's something that as a developer, if you run into, you can think you've made something good, but it'll be broken in very significant ways that aren't obvious until it's in production. And so if you have some specialized use case, absolutely pursue that. Most of the common use cases, like, hey, I want to see if these products are similar. People have solved these problems already, so you can work, you can take advantage of their effort. But if you do need to create something specialized, you need to work with the data science team closely, because they have that specialized knowledge to understand the pitfalls of how to model the problem correctly. I mean, at the very least, if you're doing like image embeddings, you need to train it on a bunch of images, or you need to take like a rip off the bottom layers or the top layers of the model and then retrain on top of that. Those are options as well. It is up. It is there. It's okay. It's loading the memes. It's loading the memes. We have memeage. Okay. Almost done. Come on. There we go. They're all loaded. So I should be able now, if we got to that local one, we can see we got all these memes in Redis. There's the image. There's the embedding. There's the title. If we go to a browser, hit localhost, I think it's 8,000. There we go. Now watch, my camera won't work. My fan is totally spinning up right now. Oh, come on. Okay, I'm gonna try shutting down the browser. Try it again here real quick. I know I'm at time. Sorry. Let's try this. Okay, Camo Studio. Don't check for updates. This is the worst possible time ever, right? And then if I can set Camo Camera, there we go. And I can tell it to use my allow, use my webcam. Come on. Come on. Of all the things for my demo to fail for. So, well, what I'll do is I don't want to abuse everyone's time, but what I'll do is I'll set this up out in the hall. If anyone wants to see the demo in action, I'm happy to show it. It really does work. You can trust me. I'm a developer advocate. So I'll just leave you with one last slide here. And just a blog post to check out. If you're interested in looking at the performance of this, we got a blog post. We did some benchmarks, and basically our benchmark says Redis kicks butt. So go check it out. I'm Guy Royse, and please go ahead and give my talk a rating out there on the QR code. You've probably done this for lots of other people, just like I totally did for everyone else. The way you do this is you scan it, and then you select the highest number, and then submit your feedback and say, Guy's talk was awesome. You should totally have him back. So this is what I got. Thanks so much. Oh, here we go. Let's okay, well, we can't not do this.
Yeah, we have a very short break now, so please find your next session. It starts in less than 10 minutes.
I can't see this on my screen, but we'll see what we get. There we go. Saved by the demo gods. Thank you very much.